Welcome to our final project presentation. My name is Krishna and I did this project with my teammate Ali. Our project topic was on representing regular expressions with generating functions. Before moving on ahead, let's talk about some basic theory regarding the class of languages. We already know that a DFA, the class of languages that is decided by a DFA, is equal to the class of languages that are represented by an NFA. This is also true for regular expressions. Regular expressions, every regular expression can be represented by an NFA. We can do this by converting the regular expression into an NFA by procedurally changing the regular expression into an NFA by looking at the state transitions. Additionally, we can convert an NFA back to a regular expression by using a transition class called the GNFA. The GNFA basically looks at state elimination, uses a sort of state elimination technique that relies on the state transitions, and as we'll see further, we'll use this method quite a bit to get the unambiguous regular expressions. Regular expressions unfortunately can be very can have a bit of ambiguity in them. This occurs when there are multiple parsing trees or multiple derivation trees to reach the same string. An example can be seen in the slide. We have the regular expression S gives AS or AB or SB. In one of the methods, S gives AB directly, and in this other method, S first gives AS and AS gives AB by the third transition. As you can see, both of them lead to the same exact string. However, they both use two different parsing trees. This indicates that the regular expression is ambiguous. Later, we'll find methods in such a way that when we are constructing this regular expression, we never create ambiguous regular expressions. Transition from DFA to Regex. Let's say we have the DFA machine M. The machine M contains like a few different parameters in form of a tuple. As we can see, the states can be numbered from 1 to n, where n can represent the set of final states. And as is mentioned in the next point, we basically separate these machines from M1 to Mk, where K represents all the different final states possible in F. And for each of those individual M1 to Mk, let's number the associated states from 1 to n. This just makes it simpler so that once we reach the Regex expression for each individual Mi, we can just combine them by just using the union operation. Essentially, what we'll do is we initially start off with the adjacency list matrix. This adjacency list matrix will contain either nothing in I, j if there is no state transition. If it does contain a state transition, we will just add a character C. This C is basically what the character was for in the delta over here. So let's just say that delta from state 0 to state 3 was a 1, and the delta from state 1 to state 4 is 0. So that's what is going to be present in that adjacency matrix, whether it's a 1 or a 0 based on what was there on the character list, sigma. After this, we're going to perform a sort of Floyd-Warshall algorithm where we iteratively eliminate this the middle state K. We start off with the state K at n and progressively go backwards all the way till state 2, and essentially we will be adding the possible transition from I to K and K to J and any sort of like cyclic states in K itself, K star. We're using the clean star operation. This way we ensure that the K state is covered for all the states in I to J before we eliminate it. And when you do K minus minus, this final Regex expression is correct for several reasons. The first reason is that the intermediate states of K will not be involved in the I to J transition until it reaches it. We can see that the k operations go from the bottom all the way till state 2. Until then, the I comma j doesn't have any of the it won't be affected by the k operation. Additionally, the clean star operation k to k is computed once. Now, notice how the values of k, the state k, is is at the bottom end of the state list. It's only when I to j has fully has all operated on all the possible eliminated states is when the clean star operation occurs. And because of this, we know that the clean star operation is correct and it's unambiguous. And it's because state I to j does the unique sort of union and concatenation. We know for a fact that the clean star operation is also unambiguous and it doesn't form this breakable sequence. The concatenation operation itself is correct, and it's if you can consider a state transition from I to j. If there was a state k that existed between I and j, obviously first the state I will go to state k, and then the k operation, the k state will have a cyclic operation to itself using via the clean star operation, and then the k to j operation will occur. So therefore, this concatenation operation makes sense. There are many different advantages to having an unambiguous regular expression. When we have unambiguous regular expressions, it's possible to we will have a single parsing method for each string. This ensures that there is consistency and reliability across in applications such as compilers and formal verification. This is also true because a lot of different languages use the same regular expression, and having an unambiguous consistent regex might be very helpful. However, on the flip side, there are disadvantages as well. By design, it's very complex to have like an unambiguous regex. Therefore, creating an unambiguous regex can be extremely challenging. It might also be performance intensive to set up these kind of unambiguous regex expressions. So now we'll define a technique where we can go from starting with a DFA machine and end up with a regex expression. Before moving on ahead, let's understand what are the requirements to actually have an unambiguous regex expression. There are mainly three points to consider. Firstly, when we finally create the regex expression, any union operation between two classes of languages should be mutually exclusive. We can imagine what would have happened if there is an intersection between beta and gamma, as shown in the example. If there is an intersection, then it is possible that one of the strings can be created by just using one of the classes and not as a union. Additionally, the second point is when we concatenate any of the two strings from two different expressions, they have to be unique. It should not be the case that one of the strings can be created by just using one of the classes and the other string can be created by the other class. This would lead we want to ensure that in order for it to be unambiguous, the concatenation should be unique. Lastly, the clean star operation can be similar to the concatenation operation, where any clean star operations applied to a string should lead to a unique concatenation of the string. DFA's
ambiguous regular expressions to a DFA. Currently, we can convert a DFA to an unambiguous regular expression. However, there is no well-known method to convert an ambiguous regex to an unambiguous one. We can convert a regex to an NFA, but converting an NFA to a DFA after that is going to be combinatorially explosive because it can result in close to infinite transition states. So, generating functions. Generative functions are excellent mathematical tools that are used to encode sequences and combinatorial structures of different discrete structures as formal power series. This also enables the use of algebraic manipulations to produce meaningful representations, facilitating singularity-based analyses. So looking at poles and asymptotes of a graph, for a language L over the alphabet 0, 1, the bivariate generating function is as follows. Function L, x, y equals the summation over from ij equals 0 to infinity, bij being the number of strings of length I plus j in L that have exactly I0s and J1s, and xi, yi being the string itself. We will look into how generating functions can be used to make regex unambiguous. So generating functions from a DFA. We can employ similar methods to convert a DFA into a generating function by first generating the adjacency matrix for an n-state DFA, M, that recognizes the language L. Assign x for every 0 arc and y for every 1 arc as the initial values of the adjacency matrix, and set other entries to 0. If M has multiple final states, create in some matrices for each final state Q. Designate the start state as s equals 1 and the final state as t equals 2 or t equals 1, if it is the start state, and apply the transformation. In a nested loop, so we're going to see a adjacency matrix generated in the following way. Aij equals Aij plus the adjacency matrix M, I to k times the adjacency matrix again from k to j, divided by 1 minus a, the matrix k to k, which is going to be the determinant, in a nested loop. Summing these results for each path from s to t yields L, the generating function for L, which remains invariant regardless of the DFA configuration or the order of state elimination, are the same as the benefits of the generating functions themselves, being able to see different enumerations and encodings of any power series, which will apply to a regular expression when it is displayed as such. So we have quantitative insights. Generating functions quantify large complexities, detailing string counts and growth patterns defined by regex. They also enable predictions on the number of strings matching the regex to up to any length, aiding in performance optimizations. The convergence properties of generative functions reveal the underlying complexity and density of the language. Analysis of function poles and zeros helps identify key language properties such as repetition, ambiguity, and variability. Generating functions also link regex analyses with advanced mathematical fields, providing deep theoretical insights and enhancing understanding of language structure. A regular expression to an unambiguous regular expression by using generating functions. Thanks for watching.